So last time we were wondering how would the eigenvalues, even just the eigenvalues of Brownian motion, feel free to do whatever you need to, would behave, the eigenvalues of the following stochastic matrix would behave a matrix n by n. We should think n as large, but it's actually a computation for fixed n, and where each entry is a Brownian motion. So each entry is a random function of time. That's how we think about it. So W11 and so on. So all these Wij, all these, so they are just random variables, but they do not take values in R like we see in the first lecture, but they take values in a space of continuous functions. Okay. And they are all these random variables, all these objects, they are independent except for the fact that Wij is equal to Wji, and actually, if you remember, we use the same normalization as for real numbers, because if we fix one special time t, then of course we come back to just a matrix of real numbers, and we have seen, for instance, the limit of its spectral measure in the first lectures. So now we think rather that they are functions, so we do not fix here number, but of course the normalization with square root of n should be the same, because in particular the eigenvalues should like converge in some sense for the same n. But as we fix n, it's okay. We can use this normalization. Why not? Okay. So what are these objects? Because there were some students who were not acquainted to Brownian motion, and stochastic processes. So we have seen, recall that we have seen very quickly some characterizations of Brownian motions where, okay, so it was a random variable, taking values in the space of continuous functions, and we have seen that it was a martingale. So this means basically that the expected value of Wt given Wr up to time s less than, for some s less than t, this was equal to Ws, provided s is less than t. So this means that the expected value of deposition of this random function at time t, conditional to the fact that you know the function up to time s, which is s less than t, it's exactly Ws. And we had also checked that what's called the quadratic variation of Wt. I mean, we gave this characterization, didn't check it, is just t. And W at time, this is not really important, but we have said that like we start in 0. So these are functions that start in 0 times 0. Or we have seen the characterization as a Markov process, so like Markov process with generator 1/2 the Laplacian. So now Markov process, we say, is like stochastic process. It's not like there is a universal definition for it, but the basic idea here, and which perfectly works for Brownian motion, is that, so it's the following characterization, that if a random variable taking value, so a random function, C0 infinity, a random variable taking values in the space of continuous function is a Brownian motion, say, if for each function f, which is a smooth, okay, so say C2 with bounded derivatives, f of w at time t minus f of w at time 0 minus the integral between 0 and t of 1/2 the Laplacian of f in Ws, ds, okay. This is a new function of t. So you give me this function of t, Wt, and a smooth function. I make a new function of t, which is this one, okay. Let me call it mt, okay. Which depends on w and on f, okay. So mt is this new function at time t is the old f of the Brownian motion of this w at time t minus f at w0 minus 1/2 the integral between 0 and t of the Laplacian of f w of s. F is smooth. This is a continuous function of t, so there is no problem to define this integral, okay? Just by Riemann sum even. So the characterization of Brownian motion as a Markov process with generator 1/2 Laplacian means that MT is a martingale for every f smooth. So the expected value of MT given MR is less than R less than S. This is MS. Okay, so this means that so in particular, from this fact, since if you take the expected value in this relation, it tells you that the expected value of MT is equal to the expected value of MS for every T and S. This tells us in particular, let me write it here. That the expected value of f of Wt is equal to the expected value of f at W times 0 plus the integral between 0 and t of 1/2 the expected value of the Laplacian of f Ws in ds. So again, what I'm saying is that claiming that W is a Brownian motion in this sense is equivalent to claim that W is it's really even or if for every smooth function, this new function of t, this new random function of t, is a martingale. Okay, it's equivalent. And or we had seen another characterization with with the finite dimensional, but we will not use this distributions of Brownian motions. But this was just to give an idea. So like of the Wiener measure of Brownian motion. This means like we fixed some window intervals or more generally measurable sets corresponding at some times. And we wrote explicitly the probability that this random function was was in this interval at time t1, in this interval at time t2, in this interval at time t3, and so on, as a long Gaussian integral. Okay, but this characterization is the most explicit, but it has no use for us. So, okay. Now, why am I describing Brownian motion? Because I want to describe some object which is even a bit more general, but not that much. So let me erase this, okay, because I want to quickly define a diffusion process in RD, okay. So we want to make a very quick, say, definition, or just to get really a quick idea what is a stochastic differential equation. Sometimes this is called an SDE, okay? So let's say we are on RD, okay? So like you have seen probably at some point ordinary differential equations. So their equation like is dot equal to B of x, okay? So so x, you're looking for a map x, let's say continuous, with values, say, in RD, satisfying this equation where B, so B is a tangent field on RD. So on RD, this is just it will be, say, Lipschitz map from RD to RD. So what does it mean to solve this equation? But for instance, it means to find the curve here such that x times for every t, xt is equal to x naught plus the integral between 0 and t of b of xs ds. Okay, so I just denote the dependence on t as an index. This is just x at time t, x of t. This is a b. Okay, and you know that probably from first year calculus that if, for instance, B is Lipschitz, then there is a solution to this equation, which is well defined for all time t, say, which is unique once you fix, for instance, the initial data. Okay, now we want to look at a slightly more, not that much, but say first, at least in this case, slightly more general problem where there is also not just B, but there is a Brownian motion added. So this means, so what does it mean, this equation? Because we have seen that, we have, say, not seen, but we have seen that we have like mentioned the fact that W is a continuous process. Yes, it's a continuous random variable, but not differentiable. So if you just read it like this, it's a bit problematic, but in reality, if you give like the usual integral representation, we just look, you give me a Brownian motion, and we just look for a random variable taking values in C0 infinity, so a stochastic, a random function, such that xt is equal to x naught plus the integral between 0 and t of b of xs ds plus wt. Okay. Okay. Wt minus w naught, but w naught we say it's 0. So just the integral form of this. Okay. What I would like to say about this process. First, when can we expect to have solutions? Well, again, if for instance B is Lipschitz, there is no problem. Let me be very informal, but like even in this case, how did you prove existence? For instance, if B is Lipschitz, you do a fixed point. So here you can do the same, because if I have two solutions, x and y, I can take their difference. Okay, okay, or I could do the same like with the so-called Picard map. But let's just see that like the behavior is somehow good. If I have, say, two solutions, and B is Lipschitz. When I take the difference of the two, Wt. So the Brownian motion disappears. So it is very easy. So to prove that this problem is well posed, actually you can basically use the theory of ODEs, because this is just a continuous function of t here. But so if you do the difference, you certainly will have something like the norm of xt minus yt squared. Okay, and say that the initial data is the same for the sake of simplicity. This will be less than, okay, the integral between 0 and t of b of xs minus b of ys ds, the norm. So I can put the norm inside. And so it should be clear that if you use, say, I can take.
I guess without square on the left.
Yes. So right. Yeah. Also, that's why exactly. So that's why this cannot be. Oh, sorry. Sorry. So I can do like something like the supremum of a t less than some fixed t, and just put a t. And so I think if you continue exactly like in this proof, just to keep in mind that this is a stochastic process. Yes, I can take the square and the square probably, and so use Cauchy-Schwarz here. I think for if this t is small enough, I think it's clear that you can close a fixed point argument, so that would work both for existence and uniqueness. So for instance, bound, say, the supremum of a t of, so this will be just the distance of square, let's write like this, between xt and yt, okay? So this will be less or equal than a constant, which can be made less than 1, because here there will be t, right? Times the same thing, okay? And so on. So in this way, it will be, you can prove that for some bounded t there exists a unique solution, and then okay, if there exists a solution up to some time capital T, then you can this capital T, how big it is, only doesn't depend on initial data, only depends on the Lipschitz constant of B, so you can continue with this solution for an arbitrarily long time. Okay, this is just, so at least when B is Lipschitz, this problem is well posed. I wanted to discuss very briefly the case of Lipschitz because we will see that our dynamics will be singular, so we need to take care about this, and which is like the interesting feature of this model of one interesting feature of this model of eigenvalues that move over time. And the other thing I want to say is, okay, what can we expect about this process? Because you see, if I know, it should be clear from this form or this form that this process should also be a Markov process. Because once I know what happens about my process up to time, say, t, to continue from time t to time, say, t plus s, I just need to know who was the process at time s. What I mean is that this, what I wrote for time 0, it will also work for later time, because xt will be equal to xs plus the integral between x and t of b of xi dr plus wt minus ws. And as we have very briefly mentioned last time, this increment doesn't depend on the history of Brownian motion up to time s. And x is in some sense just a function of w once you know b. So you see that to continue from time s to further later times t, you do not need to know who was x prior to time s. So that's a clear indication that this process should be a Markov process. So let's just try to compute who should be the generator of this Markov process, just to get an idea. So let's very informally, let's try to compute, or not so informally actually. I take a smooth function of f. Let's try to compute the expected value of f of xt minus, say, f of x0. Okay. So the short time, you should think that t is small, and let's compute the short time evolution of the expected value of an arbitrary function. Okay. So we should think that t here is small. Okay. So we write some small o of t with t going to 0, meaning. Well, so we have seen that if this was the Brownian, I just erased it, but if b would be 0, so x would be a Brownian motion, we have checked that this was just 1/2 the integral between 0 and t of the expected value of the Laplacian. Okay, so what to do in this case? We know what to do if there was just Brownian motion. So here's our process. So let's just write it as the expected value of, okay, xt is just f of x0 plus the integral 0 and t of b of xs ds plus wt. And then I should remove minus f of x0. So, but instead of removing directly f of x0, I can say remove just the somehow easy part, b of xs ds. So this part is like we understand what it is, plus the same. So in this passage, so here I didn't use the t small, but I just wrote with xt inside f, and I add then remove the same thing from this in this equality. So it's a clear equality. I continue on the other side of the blackboard. And so now let's think that t is small. Okay, let's first the easy part, this thing. Okay, so if I compute, I just do Taylor expansion, okay, for t small. So x is a continuous function of t. So integral between 0 and t is a smooth function of t. The difference between these two guys will be just by Taylor formula. It will be t times b at time. So okay, the derivative in time of this guy times the differential of f. So when t is small, this will be just b in x naught df in computed at time 0 in x naught plus small o of t. Okay, I just apply Taylor formula in t. And who will be this guy, however? So it's something plus Brownian motion minus something. So if this something wouldn't depend on t, this would be exactly this would be exactly the expected value of the Laplacian of the integral between 0 and t of the Laplacian of f in Ws. Now this thing behaves slightly, but continuously on t. So in reality, it's not. So it's not also hard to guess that this part should go as t times. This should go, very roughly speaking, as integral between 0 and t of 1/2 the Laplacian of f in this point, okay? In say xr dr. But these, just because I added the Brownian motion to xr, but this is actually t times 1/2 the Laplacian of f of x naught. So up to errors, yes. So plus small o of t. Okay. So this guy I expect to go like this guy, and this guy like this guy. So finally, what I'm claiming is that the expected value of f of xt minus f of x naught divided by t, okay, converges as t goes to 0 to b of x naught df in x naught plus 1/2 the Laplacian of f in x naught. So which is the same as saying that provided b is smooth enough, is Lipschitz, say, if I look at the equation x dot plus w dot, so this informal equation whose real meaning is I look at a random function such that this holds for every t, okay, that's the exact definition, then I could have, so we checked informally this computation, but I could have equivalently defined the distribution of this process by claiming that it's a Markov process with generator b. So a generator is an operator that acts on functions, let's call it L. So the operator associated to this evolution is let's call it LF, is 1/2 the Laplacian of f, that would take care of the Brownian motion part, plus a first order operator, a derivative BDF. Okay? So if you think of a differential equation, x dot equal to b of x, you can indeed look at it as a Markov process with this generator. That's perfectly fine. And if there is just Brownian motion, that's what you have. And if you have both, that's called just a diffusion process, okay? In general, I mean, if you give an operator with some good analytical properties on functions, you can build a Markov process. So you can build a probability measure on the space of functions of time with this property. So this is also equivalent to say, we didn't check it, but like, here we just check that the expected value, so for t small, so the derivative of the expected value goes like this operator, but this is the same actually, using the Markov property, to claim that for every function, this object, this new function of t is a martingale. So for Brownian motion, just there was no b, okay? Very good. And let's make an example, which is the most classical mean field example of a diffusion process. And this will be exactly what eigenvalues of our random matrix will do. So let's think that we have like n particles interacting. So let's say that like if a particle is in a position x and another particle is in a position y, they will interact. such that, say, the particle at x will follow. That's not really a force. We write it as a first. It's not a Newtonian dynamics. You could write the Newtonian dynamics in this way, but so like the direction the particle x follows is a function of the position of x and y. Okay. So now, if I have n, I think that each particle, so say particle I, interacts with all the others. So it will be a sum of these. Sometimes they are called two-body forces. Okay, so I have a particle in a position x1, a particle in a position x2, and so on, a particle in a position xn. Their position will be a function of the time, and I think that xi, how it evolves over time, okay, will be just the sum of all the interactions. Okay, it's called a two-body interaction. And since I'm thinking that n is large, I can just put. So if you want, I can just rescale time or put an n. So since this is a sum of n things, I divide by n just to make an order 1 thing. Okay, this would be just a deterministic interaction. But now these particles that, I don't know, they have some, each particle, so it's mean field is called a complete graph. Like each particle interacts with all the other particles. Now I put them in boiling water. So there will be also some, so beyond the interaction that moves them, there will be also some randomness due to the boiling water that make them move. So the standard way to do this is to add on each particle a Brownian motion here, in the sense of the equation we have seen there. So if each xi, say, maybe, I don't know, in R, in R2, or let's say in R, which will be our case, so this is just a dynamics. Each particle is on a line, but they interact, okay? So the whole process x, which will be just x1, xn, okay? This will be just a random function. So this will be a continuous function, random, with values in R to the n, okay? And I'm thinking that for each particle, there is an independent, so all these W1, W2, and so on, Wn, they are independent. So yes, okay, but still you see that if I look at this as a dynamics in zero infinity with values in R to the n, these n particles, it's just one equation of this type in Rn. Okay, so n will be large, but what's the problem? So if this is a Lipschitz function, for instance, this f, then we know that there is a solution which will describe the random dynamics of these particles interacting among them. Okay, that's good. It's probably all what I wanted to say on this. And of course, we can write, so like the generator of this Markov of this process and so on in Rn. Without just, it's a bit cumbersome to write all the indexes, so we will not do it now, but I mean, it's clear that this is a special case of this, for each fixed n in the space Rn. Okay, so why am I talking about this? Because the theorem I want to prove, which is a rather influential fact, is the following. So I take this matrix where on each entry there is a Brownian motion divided by n, and the matrix, they are all independent but for the fact that the matrix is symmetric. And now I call lambda 1, lambda 2, lambda n the eigenvalues. And they depend on t, okay? So there are also, so these n eigenvalues, let's call it lambda, okay? This is a vector in Rn. So it's again a stochastic process, it's a random function in Rn. So the claim is the following, that, okay, no matter how we start in reality, but let's say that we start, just for the sake of simplicity, there is an invariance of the law of this object by orthogonal transformation. So actually, with no loss of generality, we can assume that, say, lambda 1 of 0, that at time 0, the matrix is ordered. Or say, we can state it like this. So no matter the initial data, no matter the... So let's add, if we want, also, this is a matrix of all zeros at time 0. So if you want, we can add a matrix at time 0. Let's call this metric, I don't know, M of t, okay? Is this Mn of t? Is this metric of Brownian motion plus some metric at time 0, matrix at time 0, okay? So no matter the initial data, so no matter M0, the lambda I are all distinct at time t is strictly positive with probability 1. With probability 1 and satisfy if we order them by, say, that lambda 1 is the largest, lambda 2 is the second one, and so on. They are all distant. They satisfy this equation. So they are diffusion processes. They satisfy lambda dot I is equal 1 over n, the sum from 1 to n of 1 over lambda I minus lambda j, plus, so let's call them w dot I, where the w dot I are independent Brownian motion. So beware that this w dot I, okay, is a Brownian motion. So its law is the one we described before on the space of continuous functions. But it's not any of these guys, okay? It's some, if you want, it will be some function of all this Brownian motion here, but no one of them. But still, I mean, you can have random variable such that when you compose through some function, their law is still the same, yes? So this is a Brownian motion. So this means that this is a random variable with values in the space of continuous functions with some given distribution. But it's not any of this Brownian motion, okay? Just because, like, if you want, we can call it BI, okay? Let's call it BI as Brownian, not to confuse it with the entries of the matrix. And they were all divided by square root of n, not just the first one, of course. And here, sorry, there is a factor 2 of the square root of n, because I divide by n. With the BI. So B1 is independent, so you see, the deterministic part of this evolution deals with the interactions between the eigenvalues. So clearly they are not independent. To know the evolution of lambda I, you need to know where the values lambda j are. But the stochastic part, this Brownian part, is independent on each lambda I. So if we see the picture of the particles interacting before, okay? What is the picture we have? Okay, at time 0 we start as we start. It's not so important. Let's say that we have n eigenvalues. And for the sake of simplicity, we can think that already at time 0 they are all distinct. Otherwise, they will become immediately distinct for every time t strictly positive. And so each of them, say, as long as you don't consider this part, each of them behaves as a Brownian motion up to some coefficient. But then also they would like to move randomly along this real line, okay? But then there is also this interaction part, exactly like these particles in the water, with the other eigenvalues. And if you check the sign of this lambda I minus lambda j, you see that when lambda I is bigger, for instance, than lambda j, this is the term of the interaction is positive, so lambda I tends to become even bigger. So this means that the interaction is repulsive. Okay? With respect to the dynamics, where there is no this term, the dynamics with that term tends to make the eigenvalue to spread more apart. So like the eigenvalue of this matrix behaves a bit randomly because the entries were evolving in a random way, but it feels also the presence of the other eigenvalues in the way that they are with a repulsive two-body interaction. So eigenvalues of this stochastic matrix really behaves as interacting particles in a pot of boiling water. Okay, that's a bit like the picture. And what I would like to discuss briefly is, okay, we have seen that this thing here, if here I would put as a Lipschitz function of the lambdas, the solution of this equation is well posed. Now, the fact that here there is this singularity is a very specific and feature of this system that say, actually works the same also if you, I don't know, do other things. For instance, you put Hermitian random matrices here and so on. So I would quickly like to discuss the nature of this singularity, in particular, say to prove that this system is well posed, even if this drift is singular. If you like, you need to use this fact that it's repulsive in some sense, because like even in the theory of stochastic differential equations, in dimension 1, this singularity 1 over x, it's not that nice. Yeah. If you are a bit accustomed to, like, I don't know, Markov, like to elliptic operators and so on, like the generator of this Markov process, what would be more or less standard to treat here is a singularity that goes like the singularity. So this guy has a generator, the Laplacian. So here you may want to treat a singularity which is of the order of the green function of this Brownian, of the Laplacian. So the derivative. So like the green function is logarithm singularity in dimension 2, so the derivative is like 1 over x. This would work nicely in dimension 2, not in dimension 1. But in reality, since this interaction is repulsive and it's a very, I don't know how to say, a very specific type of interaction, we will see in a moment how that it works very nicely, and one can find immediately a Lyapunov function for this object. But I would like exactly to give a very brief sort of physical description of this thing. So
just to compare it with what was before. In this scaling, lambda i's asymptotically belongs to the half circle law on what segment?
Yes, right. So this it's a good point. Thanks for the question. Indeed, last time, so the first lecture, we checked that if the entries are IID with n, okay, I divide them by square root of n, and the variance is 1, they go to semicircle law. And then we remark that if the variance of the random variables is t, okay, they go to the semicircle law with square root of t. So here we'll go minus square root of t to square root of t, like this. So they start in 0 and then they spread as the square root of t.
Just like the Brownian motion itself.
So for exactly. So for each t, we know the limit. So this we already. About these eigenvalues, what do we already know? That for each fixed t, if we do this 1 to n delta lambda I of t, this will converge to this. Let's call it sigma t of x dx, where sigma t is this density. Semicircle between minus 2 square root of t and square root of t. We wrote explicitly the distribution with t last time, indeed. But here we want something different, using the fact that they are really Gaussian process. Namely, we really characterize exactly the evolution of the eigenvalues, a fixed n. So there is no limit here. It's really a fixed n. So if I have a Markov process, like all these Brownian motions, the collection of all these Brownian motions, is not, in general, a function of this Markov process, will not be a Markov process. But this like complicated function, like the roots of the characteristic polynomials, so that are the eigenvalues, surprisingly, they are again a Markov process, and we can. So I don't need to describe like the law of the lambda I. I don't need to refer to the original Brownian motion. So they just have an evolution which is consistent by itself in some sense. Yeah. So you see here. Even, let's say more in general, just to connect to this remark. Suppose that I do this, x dot is 1 over n f sum, like we were doing before, like the example of the particle, f of xi xj plus, okay, like here maybe the Brownian motion is small, 2 over square root of n w dot I, okay? And now, suppose that I also know, like I do in this case, that 1 over n, the sum of delta, sum j from 1 to n, xj of t, converges to some given measure, which depends on t, sigma t. So this is, for every n, this is a probability measure, a random probability measure over R. But when n goes to infinity, exactly like we know in this case, this converges to a deterministic probability measure. So this is, for each t, this is a probability measure over Rd, okay? We already checked in the first 2 lectures that for each t, if I put here, if I don't put the whole function here, but just its value at a fixed given time t, this is just a matrix of real numbers. Random real numbers. So for them, we have checked already the semicircle law. So we know that the spectral measure converges to this semicircle distribution. So here, this we know, okay? For each t, as n goes to infinity, we have this convergence. So if we do this, if we know this, what can we guess about this xi, say x1? What can we guess, for instance, about x dot 1 of t? Okay, well, you see that we have called this pi n, this measure. You see that xi dot of t, this is nothing but the integral of, so let's call this is nothing but f pi n of x1 plus square root over 2n w dot I, where f, for a given probability measure mu, f mu of x just means the integral of f of x and y in d mu of y. Yes, because when I integrate with respect to this measure, f of x and y, so like if I do f pi n in a point x, just by the definition of this measure, this is just 1 over n, the sum over j from 1 to n of f in this point x and xj of t. Oh, so this also depends on t, sorry. So, no, okay, pi n of t here. Okay, so, okay, now we should check that anything is continuous. Certainly I would need that this f is say, somehow smooth enough, but if I look at this evolution, okay, and we take n to infinity, so exactly as we know for this measure going to sigma t, integrals of function will converge. Okay, so I would expect, looking at if I know the convergence of the spectral measure, and I look at these dynamics, I would expect that say x dot 1 in the limit when n goes to infinity will converge to the following deterministic dynamic: x dot equal to f sigma, so f dot at time t, f sigma t of x1. So I just take my two-body interaction potential and I integrate it with respect to the limit of this measure. It's not so, let me write it again because it's very confusing. Oh, it's there, little patches on the blackboard, sorry. So I have, if I look at the equation x dot I, so I have these n particles that interact, f of xi, xj, sum of j, xj plus, like we had, let's put the same number, square root of 2, w dot I, okay? And then I define, for a given probability measure mu, f mu of x in a point x, the integral of f of x and y, and the mu of y. So 1 over n, sum, in this notation, sum j from 1 to m of f in the small point x and in xj of t, whoever it is small x, this is just f pi n of t in x. So what's the picture? Okay, let's finish to try this. F pi n of t. So since pi n goes to sigma, pi n of t goes to some sigma t, which is a probability measure on Rd. And this convergence happens exactly in the sense that it makes integral converge. Okay, the limit when n goes to infinity of so let's call this x depends on n. Okay, all this x depends on n. They satisfy an equation that depends on n. As n goes to infinity, I fix one particle, say the first one, x1n. I expect that this converges to some x1 limit. And what will be the equation for x1? Well, x1 dot should be equal to, okay, here there was f pi n of x1n. Okay, all this is f pi n of x1n. So pi n is converging. If xn is also converging, there I should have f sigma t in x1. And then, okay, this noise had the square root of 2 over n, so it will vanish in the limit. So I will just finish on a very close. So as we remarked, if this kind of result didn't tell me anything about one given eigenvalue, or maybe 2 or 3 of them, just discussed like all together as like only relevant non-negligible fractions of n of eigenvalue can play a role in the limit of this measure. Here, I am really able to compute what happens about, say, the largest eigenvalue, a fixed one of them, or maybe the second, or maybe the first 10, and so on. If I use instead of x1, I don't know, x1, x2, and x3, and so on. So, what is the picture? Here we have these n, n particles interacting all together. Now I just follow what happens to one of them, okay, when n becomes larger and larger. When n becomes larger and larger, if like the dynamics is regular enough, they will, exactly like the spectral measure did, they're like if I put, if I think that each particle has a weight 1 over n and I pass to the limit, I will see in the limit n goes to infinity sort of a continuous distribution of mass. But now I have my fixed particle, which kept interacting with all the particles in the limit, will interact with this distribution of mass, and the interaction between x and the distribution of mass will be described by this function. So you see that once I give this mean field characterization of the dynamics of the eigenvalues, it's extremely powerful, and I can very easily at least guess what should be the limit of the dynamics of various eigenvalues. So now, for instance, if I fix time 1, my matrix of random Brownian motions will be just a matrix of random variables with variance 1. But still, so for instance, I can describe for it what what is the law of the largest eigenvalue. It's just the solution at time 1 of this equation, where f of x and y is 1 over x minus y, and the mu is, and sigma t is just the semicircular law at time square root of t. So with between minus 2 square root of t and square root of t. So I can write the integrals, the equation, solve, and find quite easily and very explicitly, if I want, all the dynamics, and I can understand then, I don't know, how far xn from this limit x1, how the difference goes, and so on. I have a very explicit and detailed description, which is exact for every n. So, okay. In all these, so if f would be really actually continuous, say Lipschitz, it would be immediate to do all this computation in a rigorous way. Here, all the technical difficulty comes from this singularity, because let me write again. We want to prove that the eigenvalue satisfies the equation lambda dot I is 1 over n, the sum over all the j different from I of 1 over lambda I minus lambda j plus square root of 2 over n w dot I, where these are b dot I, where these are independent Brownian motion. Okay, so I want to dedicate still a bit more time to this problem, but I really don't want to discuss too much like the technical details for the singularity, except here at the beginning, just to check how to get them under control. And we do it once, and then we pretend that it will always work like this. So what's the problem here? Even just to define that, so then there will be a theorem that we will prove maybe a bit next time, that the eigenvalues converge to the solution of this equation. But first, let's check at least that this equation is well posed, because I said, okay, it's a very easy fixed point if here you have a Lipschitz function of lambda. So this is, okay, if let's do, I don't know, vector lambda, like lambda 1, lambda n. Remember that we ordered in such a way that this is the largest, the second, and the third, and so on. So this dynamics is some lambda dot equal to some function of lambda we had called b plus Brownian motion. Okay, square root of 2 over n b dot, where b dot is just the vector b1, b2, and so on. If this would be a Lipschitz function of lambda, there would be no problem yet to have existence. But we'll see immediately that here there is this singularity. So how to get rid of it? How to prove that this system is well posed, that we can find a solution which is actually global in time, and so on. Look, the idea is just the fact that this is a gradient flow perturbed by some noise. So even without noise, let's just think. Let's just make a small detour. So let's think that we have an ODE, for instance. Yes, x dot equal to minus the gradient of v of x. Okay. So with the very special tangent field, a gradient of a given smooth function v. Very standard computation. If I do v of xt minus v of x0, this is the integral between 0 and t of dv in xs x dot s. So this is minus the integral between 0 and t of the gradient of v squared in xs ds. So you see that xt, v of xt is a decreasing function. V of xt minus v of x0 decreases. So here, if you want to use general theory of ODEs, you would need that, I don't know, the right-hand side is, say, Lipschitz to have well posed of the equation. But in reality, if the equation has this form, even if v goes, say, to infinity at plus infinity, very fast in such a way that is not Lipschitz, certainly there is no problem to define a solution to this equation, because the important thing is that, like, locally you are regular enough. Since xt is decreasing, v of xt is decreasing over time, you will never visit the regions where v becomes bigger and bigger and causes you problems. Now here the picture is not exactly the same because of these. Because actually this is a repulsive force, so it could send you to infinity, not call you back from infinity. But thanks to the noise, this will cause no problem. But the idea, the approach is, to prove it is more or less the same. You just build a Lyapunov function for these dynamics. So let's first, so lambda, this will be a vector in Rn, right, for each time t. Lambda of t, okay, will be a vector in Rn for each time t. And so let's, instead of using this function, let's introduce a function which is equal to this one when lambda and lambda j are, say, a distance more than some epsilon, and then some smooth functions if they are a distance less than epsilon. And then what we will check is that the probability that this system, which depends on epsilon, will ever have two solutions, two eigenvalues, to lambda I at distance less than epsilon up to a given time t goes to 0 as we take epsilon to 0, and we will see that this is enough to say that the solution is well defined global in time. So let's define a function phi, let's call it phi r of, say, x on Rn. Okay, I'll try to stick to the lambda are the random objects, and the x are just the points in Rn where I define functions, not to create any confusion. So this will be just 1 over x. If x is, say, less than 1 over r, okay, and something smooth. I think it's more or less standard to take r square x. If, sorry, this is x is bigger than 1 over r, if x is less than 1 over r. So like for x large enough, it's exactly what we want, but instead of going to infinity like this, we send it to 0, for instance, okay? So for each given r, this is a Lipschitz function. So I can look at the dynamics, let's call it lambda r, I 1 over n some j different from I 1 over lambda I, or I can do over all the j's actually, because now this function will be 0 and 0 over all the j from 1 to n of phi r of lambda I minus lambda j plus the square root of 2 over n b dot I. So these guys are well defined. If you give me some initial data, there is a unique solution to this equation.
There is a dot on the left.
There is a dot on the left, sure, thank you, and here as well. Because it's a diffusion process, we have very briefly checked that it emits a unique solution through a fixed point. So for each given r, there is no problem. And then I look at what's called the stopping time. I look at tau, given r, positive, I look at tau r, which is, so this is a function, if you want, of the Brownian motions, let's say of the Brownian, on our probability space. It's a function of the Brownian motions, or if you want, it's a function of the lambda I. Tau r, which, if you want, is the tau r of lambda, the solution, actually, even better, sorry. Let's define this as a function of 0 infinity with values in Rn. Okay? With values in 0 infinity. So tau r of a curve here, okay, a function here, okay, x1, x2, xn, this will be the infimum over all the time positive, such that the infimum of I and j, I different from j, of xi minus xj is the first time this is less than r. Let me write it properly. Xi minus xj is less than r. Okay, so I have these r points that move over time. I don't know what they do, I can define this for any function. The first time where two of them are at distance less than r, that's the time tau r. Okay? So this is a stop in time. What does it mean? This means that the set of all x such that tau r of x is less than t is measurable at time t, so for each t. So this is in the sigma algebra generated by the projections up to time t on this space. So it just means that this is some function of x up to time t, okay, not later, okay. This event as an event, okay, is a function only depends on x up to time t, okay. You can introduce here filtration and say that this is measurable time t. But it's clear, it depends on x only up to time t, not later. To know if tau r arrived, if this time arrived at time t, you don't need to know x after time t. It's enough to know x up to time t, okay? To know that tau r is less than t. That's a crucial property of this time. And then, okay, and then let us introduce a function that in the case which I raised where of the ODEs x dot equal to minus the gradient of v was the role of the function v. And this function will be, so let us introduce this function from Rn to R. So f of x, of a vector x, x1, x2, xn, is 1 over n, the sum of xi square minus 1 over n square, the sum over I different from j of the logarithm of xi minus xj. So these are small x, xi minus xj. Okay, I have this function f. We, instead of Rn, we could equivalently even just to define, you see this function only depends here on the differences, and also we ordered the eigenvalues in this way. We could define the space, I don't know, Dn, the x in Rn, such that xi is bigger than xj, okay? Okay. So this function is bounded from below. You see, let's logarithm of x minus y, or maybe even like this. This is less than the logarithm of 1 plus x, maybe like this, plus the logarithm of 1 plus y. So f of x is, so this x is a small x, will be bigger than 1 over n, the sum of the xi square, so that there is a minus, but here we have 1 over n squared, the sum of the log of 1 plus xi, log 1 plus xj, sum over I and j, so I was different from j. This just makes n minus 1 times with a 2 the same thing, okay? If you plug these inside here, you get log of 1 plus xi, log 1 plus xj, so the sum over I and j are twice the same. It's twice the same sum, and that's how you get the 2. But then, okay, xi, of course, xi minus log of 1 plus xi is bounded from below by, I think I made the computation, it's like something like, it's bigger than minus 1. So this is like bigger than xi squared minus twice the log. So this is something like bigger than minus 1, I think. So k is a function which is bounded from below. But also check that, so if, say, if f of x is less than some constant, let's call it m, then xi minus, then for all I j, different from j, xi minus xj will be more than 1 over r, okay, where it's not important who is r as a function of m. I just made more or less the computation. I hope I was correct. I got n square m, or say r is anything bigger than this, okay? So why? I mean, like, if so, the function is there. Is the sum of the squares minus the sum of all the logarithms. Is this function, how can this function become big? Either the xi are big, or the two of them are very close. But you cannot compensate, you cannot compensate two of them close. You cannot make it like small, or say less than, you cannot make the function less than m if there is even just one pair. Of course, for m large, I'm thinking here. But if there is just one pair, that, yeah, maybe m, I take m bigger than 1. This doesn't work on B prime 0, okay? If there is just one pair that is too close, okay, you cannot compensate the fact that this minus log will be big using the logarithm of the others, because the logarithm of all the others, if the logarithm of all the others are big, so minus the log compensate the log of the small pair, then of course these squares will force all the other, will make the function big again. Okay, so like if you use again just this inequality on all the pairs, say but one, the pair xi and j, which is the closest one, with the modulus of xi minus xj, the smallest out of all of them, you can easily check this. Okay, this is just exercising in calculus 1, okay? That the xi, xj cannot be close if the function is bounded. I got this, maybe I don't claim that it's sharp, but okay. You find, yeah, so you find, for instance, this kind of computations in a book by Guionnet and Zaitouni, but it's very late in the book. It's toward the end, so it's around page 300 or something like this. So they make the thing for beta ensemble, the computation for beta ensemble, which is the largest class of matrices where basically on this, on the Brownian motion, instead of having square root of 2 over n, you have square root of 2 over beta n. So beta is like the inverse temperature. So it looks a small change, it's not. So you get a bit of simplification as we took beta equal 1, which corresponds to this matrix of Brownian motions. But if you want to check the more general computation, you can just check it there. And certainly they have a worse R, but it's not important at all for this computation. And okay, so we introduce this f, and then we introduce also then tau m of x, okay, like tau r. This will be instead, let's call it, I don't know, tau m and r. Yeah, let's call it still not tau, but sigma is also bad. Yeah, let's call it tau m of x. This will be the infimum. I use a very bad notation, so just if it's an m, it's this. If it's an r, it's that. Is the infimum over all the t such that f is bigger than m. Okay, so exactly as before, but for this function, not for this infimum. Still, you see that if I take r, if r is bigger than e to the n square m, then tau r is bigger than tau m. Okay, due to this fact. Okay. Now, up to the time tau r, up to this random time, tau r, our system coincides. So we had this system lambda dot of t equal to phi r of lambda plus b dot I square root over 2 over square. Oh, sorry. 1 over n lambda I sum of phi r of lambda I minus lambda j plus b dot I. And our original system, lambda dot I of t, 1 over n, sum j, different from I, lambda j minus lambda I plus b dot I. Now, if t if t is less than tau r, so up to a time t less than tau r, the two systems coincide. So again, this time tau r is random. It depends on the lambdas, okay? So, but it's not important, okay? Because again, it's like you observe the system, okay? And you know at time t, you know if tau r is bigger than t or not, because it was a stop in time. So you can observe this system evolve. There is no problem to define it because it's Lipschitz evolution. You see it, and you look at the time t. Is tau r bigger than that? If yes, you know it at time t. These two systems coincide. Okay, so there is no there is no problem. So we claim that the limit when r goes to infinity, that the probability that tau r is bigger than t is 1 for every t. Sorry, no, we claim something bigger, stronger. We claim that the probability that the limit when r goes to infinity, I'm sorry, that what I wrote was that tau r equal to plus infinity is 1. Okay? So tau r was a number between 0 and infinity, and we claim that when r goes to infinity, this goes to infinity. So why this solves the problem of the what's called a strong solution to this problem? Because like we have our space, probability space, that you can think is C0 infinity with values in Rn, and we are saying, okay, there are all the paths for which tau r is no bigger than 1. Then there are all the paths for which tau r, all the paths for which, better not to do it like this. How to say? I want to look at this system, okay? So up to time t. Let's say up to some time t. With probability 1, I can let's put it like this. Up to a set.
So then the stopping time increases to plus infinity.
Yes.
And for some r, it is quite larger than this t, and then our process with this r coincide up to time t.
Yeah, but you're right. But yes, exactly. But for each r, of course, there is a probability, a set of probability non-zero where you will be, but this, yes, so you can, like, you know, to say, yes, you are quite right. Like, I fix a time, this is increasing tau r, so I fix a time, let's say that we fix time capital T, yeah, we fix time T, we want to define this process up to time capital T. If we do it for every T, then that's how we define our process on continuous function for arbitrary T and for everywhere. So for this given T, okay, this is tau 1 less than T. There is a large part of probability space like this. Then tau 2 less than T. Sorry, bigger than T. So the more I increase the R, and the bigger is the portion of the probability space where tau R is bigger than T. And so here is certainly well defined. On all the paths here, on all the, say, Brownian motions here, so all the Brownian motions such that tau with r equal 1 is bigger than t, I have no problem to define this process because it coincides with this one, pathwise. And then, okay, but then there is some part of the probability space which are left over. So still with tau 2, I can hit another chunk. With tau 3, I can hit another chunk, and so on. Where does this remain non-defined because it doesn't coincide with this for some given r? Only on a set of probability 0. Okay, so for each set with positive probability, you can choose r large enough so that these two systems just coincide. Okay. No, sorry, with positive but not equal to 1 probability. You can choose an r. Okay. How to do it? Okay, we said. Let's look at okay, any of these two. Let's look at say this process x dot equal to b of x plus w dot. Okay. Again, since this guy is a martingale, so this guy is a Markov process with the generator we have seen at the beginning. For each smooth f. Now let's not, yes, for each smooth f, we have that f of xt is equal to f of x naught plus the integral between 0 and t of its generator, so b of xs df of xs plus, in this case, 1/2 the Laplacian of f of xs ds. So this minus this was a martingale, so this is equal to this plus a martingale. Good. So let's compute this thing for these, or up to time t less than tau r equivalently d, for any of these two for time t less than tau r, and this t, and the function, the one I wrote before. So f now so I take for b of x the vector field whose component I is 1 over xi minus x is 1 over n, the sum of 1 over xi minus xj, and f of x, what I wrote, 1 over n, the sum of the xi square, minus 1 over n square, the sum of the log, j different from I, xi minus xj. So, so why log? Because the derivative would be 1 over x. Yeah, let's compute this. The fact that this plus this is a martingale. Okay, so we have that f of lambda t. Okay, so and let's us take t less than tau m, which was actually less than tau r, provided there was a relation between r and m I wrote before. So that those two systems coincide up to this time. So we have that f of lambda time t, okay, is equal to f of lambda 0 plus, okay, so this computation I did it. I just need to find it. So I don't find it. Okay, sorry. So what we need to compute? We need to compute the derivative. So the derivative of f in the component for the component xi. Okay, this is okay. Okay, let's the sign will go okay. Don't worry about the absolute value, but this will be so 2xi over n minus 1 over n square. There is basically xi divided by there is 1 over sum over j xi minus xj. I'm slightly cheatly with the sign, it's not a problem. And so then if I do the Laplacian of f, okay, I have to do another derivative. So it's better to introduce these two functions. ui of x is just the sum of a j from 1 to n of 1 over xi minus xj. And vi, so this, I call it vi of x because so vi of x here is a fixes the it component and sums of the others. And vi of x is the same thing but over the squares. With the square. So if I do then the Laplacian of f, I have to derive this with respect to xi a second time and do the sum. So it's 2 over n, the sum of 1 plus, so this one just with this. So this 1 plus 1 over n square vi of x. And then, okay, this is, then I have to sum bi, which is basically 1 over n ui times dif to make this, and the Laplacian's there. So here I will have integral between 0 and t. So, no, well, before doing this, let's notice something. Let's notice that, so ui square is not vi, because this is the sum and so on. But the sum of ui square is equal to this over I, is equal to the sum of vi. So it's not that ui square is vi, but the sums are equal. Why does this happen? Because so let's compute the difference, the sum of ui square minus vi. You see, so this is a square of sums. So this is the sum over all the j different from I and all the, say, k different from I of 1 over xi minus xj times 1 over xi minus xk. That's how I wrote, this is the square of ui, the sum over, and then I sum over I. So it's the sum over all the I, j, and k, with j different from I and k different from I. But look, who is the sum over I of vi square? Is the sum over all the I and j of this square. So, like, when I do this thing in here, here I'm summing over all the I, j, and k, 1 over xi minus j, 1 over xi minus xk. And some of these terms will have j equal to k, okay? And because j is different from I, k is different from I, but maybe the j is equal to k, not different, important is not I. So I will have 1 over xi minus xj squared. And that's exactly the sum over I. These terms that repeats where j is equal to k are exactly the sum over I of vi. So here, if I do the difference, I just get the sum over all the I, j, and k that are all different. So I is different from j, I is different from k, but also k is different from j. And there is 1 over xi minus j, 1 over xi minus xk. And this I can write as the sum over the same thing of, so 1 over xj minus xk, that wasn't here, and here I do 1 over, I hope, xi minus, I want to write it in this way, x, xk. Sorry for my x, I should change the chalk just. Hopefully it's correct. So I do xi minus xj, xi minus xk, xi minus xj is the same, and I get xi minus xj minus xi plus xk. There is a minus. So there is a minus, But then, so here I can put a plus to make xj minus xi. But you see that once I do the sum of all the I, j, and different from k, each of these two guys is the same as here, because it's xj, it's first index, first index, first index, first index. Yes, and so that's this times this is exactly this. And here there is xj minus xk, okay, this is minus xk minus xj minus xk minus xi. So each of these two things is the same. So this function is also equal, let me write it here, sorry to continue here, to minus twice the same, to minus twice the same thing. So it's at 0. Which is like the miracle why we chose this function, okay? And similarly, if I do the sum over I of xi ui, this is a constant, which is n minus 1 over 2, I think. Because this is what? This is the sum over all the I and j of xi over j different from I, xi minus xj. But this again, if I do minus the sum over, so this function plus the sum over I and j of xj divided by xj minus xi, which is exactly the same function because I just changed the role of x and j. So you see that the sum is sum of 1. I sum n. Yes, it's correct. I sum. Yes, I sum n times n minus 1 of them, and so that's twice this function. So there is a divide by 2. Okay, so once I put all this computation in here, so this function is really the miracle function for depth dynamics. Okay, it's a very clean Lyapunov function. I get, so when I do the sum of bi dif, so dif was here, bi, the component I of b is just ui, so I get some constant, okay, which is here. Then I get minus the sum over ui, which goes exactly away with this sum of vi in the Laplacian. So we have a sum over I of the vi in the Laplacian, and the sum over I of ui times ui, so ui square, in here. So they just simplify, the sign is the good one, because here there is a minus, here there is a plus. So this just kills exactly this, and this times bi makes a constant. So all this thing is actually, for each x, no matter who is this x here, this thing is a constant. And this constant is not important, it's like 3 or 3n. I think it's like 3. It's 3 minus 1 over n ds plus a martingale. Okay, plus a martingale. So, okay, this is just, so f of lambda t, let's write this, f of lambda t is less than f of lambda 0 plus 3t plus a martingale. Now, a martingale, as you may have seen in some classes of probability, has the following property. So, not only if mt is a martingale, the expected value of mt is equal to ms for every t and that. So in particular is equal to, say, the expected, sorry, is equal to expected value of ms, so say is equal to the expected value of m0. For us at time 0, this martingale is 0. So in this case it's 0. But we can have a stronger statement than this, that if tau is a bounded stop in time, the expected value of m tau is equal to the expected value of m0. So in this case it's 0. You have probably seen this for like games, yes? Is there, like if you play a game, like we did the other time, I don't know, every time you make a sum, for instance, think of something discrete to get an intuition on this, on xi. And each xi was maybe +1 or -1. So you make a game, and every time you can win or lose, I don't know, what you bet, for instance. So maybe there is a, okay, some alpha I. Every time you bet alpha 1, alpha 2, alpha n, and so on. And these are +1 or -1, like you win or lose what you bet, but with probability 1/2. So this thing will be a martingale, they are independent, and you can like, is there any strategy to make money, like the expected value, on average, like the expected value is positive. Since this thing is a martingale, if you stop to play, like for instance, if you use a strategy that only depends on the result up to the time where you use it, the expected value will always be 0. And if it was a sub-martingale, on average you lose, you will always, super-martingale, you will always lose, so on average. So that's exactly the same idea. Like if you want to play a game and on average win, you need to play for an unbounded, for a time which is very long. Like for instance, you stop once you you want at least, say, 1, then this stop at this time, the expected value of, if you stop at the first time, your total budget is positive, so the first time you win more than you lose, the expected value will be strictly positive, but the time where you play cannot be bounded. There is a probability, for each t, there is a probability that you have to play for a time longer than t. So, say any strategy you can achieve in your lifetime with probability 1 will not be winning. Yes. So that's why this is very intuitive. That's why I made this story, just to tell you that this is Doob stopping theorem. You may have seen, at least for discrete time, some classes of probability, but it's actually an intuitive statement. Okay, so our stopping time tau here to kill this martingale will be t minimum with tau r, with tau m. So we fix m large, and will be the minimum with a deterministic time t and the tau r. So we check these. Okay, we have this bound. We compute it at a random time t, which is the minimum between, okay, a fixed deterministic time, which is still called t, and tau m. The first time the function was bigger than m. So, and we take the expected value. So we have the expected value of f of lambda at time t minimum tau m. Let's do the minimum like this, as is no bigger than, okay, let's say that lambda 0 was given. That's the initial data. F of lambda 0 is what it is, plus the expected value of 3 times the expected value of t minimum tau m, plus nothing, because the expected value of the martingale is 0. So, okay, and this is no bigger than f of lambda 0 plus 3t. The expected value of the minimum between tau and tau 1 is no more than t. So, what we do now, the probability then that tau m is less than t, let's fix t, and then this is equal to the probability that it's actually equal f of lambda at time, so this lambda is the vectors of all lambdas, t minimum tau m is bigger than m. Yes, because so tau m less than t means that the first time the function was bigger than m arrived before small t. So if this happened, f at this time will be exactly m. So it's indeed bigger or equal than m. If tau m is instead strictly bigger than t, this means that up to time t, the function was always smaller than m. So in particular, f at the time t minimum tau m will be smaller than m. So that's an equality, actually. Now, just to make this positive, I can add +1 on both sides. And now for this I just use Markov inequality. So let's continue here. So that's not an inequality, that's an actual equality. So let's continue on the next blackboard. Let's continue on the next blackboard. And by Markov inequality, see, I added one. F was bounded from below by -1, so this is positive. So this is less or equal than 1 over m plus 1. The expected value of 1 plus my function lambda at time t minimum tau m. But this was less than, okay, 1 plus f of lambda 0 plus 3t. So that's probability tau m is less than t. So the probability that tau m is less than t is bound, oh, let's do this, tau m square. Instead of m, let's compute it at time m square, or at time small n square, let's call it. Okay, m square. Is bounded over m plus 1. Is bounded by 1 plus 3 f of lambda 0 plus 3t divided by 1 plus m square. So so the sum over m from 1 to infinity of the probability that tau m square is less than t is finite. Okay? Because the series of 1 over m square converges. So by Borel-Cantelli lemma, tau m square less than t can happen only finitely many times with probability 1. So by Borel-Cantelli, the Italian word I struggle to write, the limit when m goes to infinity of tau m, so the probability tau m less than t is 0, okay? So which is the same as saying that the probability that the limit when m goes to infinity of tau m equal to infinity is 1. So now we have the tau. So if you remember, if we took r equal m to the n square m, or any function going to infinity of m is not important, this one.
I guess here we can not only use Borel-Cantelli because our events are included in one another, so we can just say that the probability goes to 0 and then...
Yes.
Okay.
Yes, it's a monotone sequence in m. Yeah, it's just monotone. Yes, tau m was the first time the function exceeded m. Yeah, right. Thanks, yes, absolutely. So, indeed, I was a bit confused by the use of Borel-Cantelli here, because indeed, once you have this, right. So since this is a monotone sequence of n, yeah, thanks. We get that what I actually wrote, so that the probability that the limit when tau goes to infinity of tau m less than t is less than t is 0, which means that tau m goes to plus infinity almost surely, all in subset. And no, this is monotone. And tau r was, okay, I used a bit this bad notation, but this also tells me that tau r goes to plus infinity as r goes to infinity, which is what we wanted to check in the first place. So I think it's a good point to stop. And because I wanted to prove this before the theorem, because as opposite to the proof we did for random variables, we will do a backward proof. So we start from the law of the eigenvalues and step by step checks that we build back the matrix and not the opposite way. It's much simpler to do it like this. So it's nice to have at least an equation which is well posed well, but you have seen like how you can deal with the singularities. for the remaining lectures, I will always pretend that 1 over x is a smooth function. Okay, thank you.